Testing, testing, testing. Okay, Java, continuing with chapter 6. We're looking at our required program assignment, and it's on the bottom of page 238. Define a method hypotenuse. It calculates the hypotenuse of a right triangle when the lengths of the other two sides are given. The method should take two arguments of type double and return the hypotenuse as a type double. Incorporate this method into an application that reads values for side 1 and side 2 and performs a calculation with the hypotenuse method. Use math methods power and square root to determine the length of the hypotenuse for each of the triangles. See figure 6.15. So we're given the information that we have our first triangle. Side 1 is 3.0. Side 2 is 4.0. We're supposed to calculate the hypotenuse. Triangle 2, we're given side 1 to be 5.0. Side 2 is 12.0. Calculate the hypotenuse. And triangle 3 in our test data, side 1 is 8.0 and side 2 is 15.0. Now, let's refresh our memories just a little bit with what the hypotenuse is. I'm sharing a website. Math is fun. And there's some information here. Over 2,000 years ago, there was an amazing discovery about triangles. When a triangle has a right angle, that's a 90-degree internal angle, and squares are made of each of the three sides, then the biggest square has the exact same area as the other two squares put together. This is called the Pythagorean theorem and can be written in a short algebraic equation of side A squared plus side B squared is equal to side C squared. Remembering that side C is the longest side of your right triangle and A and B are the other two sides. There's more information here, a couple little short videos if you care to look at that, and I'll share that link with you on the website. So we have our formula. Given a right triangle, side A squared plus side B squared is equal to side C squared. And side C squared is the hypotenuse. So we're looking at input via the keyboard. Side 1 and side 2 are going to be input via the user at the keyboard. And we want to continue to calculate the hypotenuse for scenarios of interest for lengths of side A and side B. I'm also noting that A squared plus B squared is equal to side C squared. Now, the length of side C is C in length, not C squared. So if I can find C squared, I can find the length of C would be equal to the square root of C squared. So I'm not solving for c squared, I'm really solving for c, which is the length of the hypotenuse. So I'll have to get the square root of this c squared result once I calculate that formula. So let's kind of sketch a design looking at some logic. This is going to be class triangle. We're going to start with a main method. It is an application. Here's my begin main and an end main. I have two sides, side 1 and side 2. They are of type double. I need to prompt the user for the length of side 1. I'm going to assign side 1 then. And while side 1 is greater than 0. So I have a positive length. It can be a double value for side 1. You might want to name your variable side A and side B. That's fine. It's certainly up to you. We're going to prompt the user for the length of side 2 and assign side 2 a double value. And then print a formatted string. The hypotenuse is, we're going to print the string, hypotenuse is, formatted new line, and we're going to call our method hypotenuse. Remember, this is hypotenuse, the name of the method, followed immediately by a parenthesis. That way we know there's no space there. That's the name of a method, and we're going to pass the current value of side 1 and the current value of side 2 as double values to the hypotenuse. So right now, this is in a waiting state as control is passed to the method hypotenuse. And our method hypotenuse is public static, so it's public. It can be called by our static main method. It's going to return a double. That's return type that this method's going to return to the calling environment. The name is hypotenuse, and it's expecting a double to be passed and assigned to its local variable side 1, and a double to be passed from the calling environment to be assigned to side 2 as a local variable. Double hypotenuse squared. Hypotenuse squared is a variable. It's of type double. Is equal to math.power. Now remember math.power. It's in the math class. Its generic form is base raised to a power. So I have side 1 raised to the second power. That would be side 1 squared plus math.power, math class, method pow, open parentheses. Base is side 2, so side 2 is raised to the second power. And our hypotenuse squared is c squared equals a squared plus b squared. So I have my hypotenuse squared is equal to side 1 squared plus side 2 squared. So there's your Pythagorean theorem. And we've solved for c squared. Now we want to solve for c, which is the length of the hypotenuse. So we're going to return math.find the square root of, pretty bright here today. See if I can darken that a bit. Okay, now we need to return to the calling environment our double value from math.square root and find the square root of hypotenuse squared. So now we're finding the square root of c squared, which is c, the hypotenuse length, and we're going to return that as a double to the calling environment. And then we're at the end of our method hypotenuse. So control transfers back to the calling environment. Hypotenuse has a result, and it will be printed in our formatted string. We're going to prompt the user for the length of side 1 for another scenario. Remind the user how to exit your while loop. Side 1 is going to be assigned the next double input value from the keyboard. We're at the end of the while, so we go back to the top of the while and test is side 1 greater than 0, a positive double value. Be sure to prompt your user accordingly to enter a -1 as a sentinel value to trigger a false test. Now, notice that here main is the main processing. We assign and declare our variables. We have our while driver that calls the hypotenuse method, but the method itself, the coding of the method, resides outside the main method. So I'm at the end of main. These are the driver, the logic for the program. The methods lie outside of main, and I have my first method hypotenuse. You might have several methods that lie outside of the main method, but before the end class triangle method. So just a reminder for placement of your method code, method or methods code. So let's look at NetBeans. All right, I'm just going to close anything that I had open in the past. That means it's working a little bit slower here for me today. I'm going to open a project, and this is exercise 6.15. And my source code is triangle.java in my project window, and it opened with triangle.java being displayed. We're going to input java.util.scanner. We're going to expect to input some variable input via the keyboard. A public static void main, begin and end. You should document your end main method. Scanner variable is input for a new scanner value input from the system keyboard. We're declaring side 1 to be double, side 2 to be double. System.out print to the user, enter side 1, negative to quit. So could make your prompts a little more friendly. Side 1 is assigned the input as a double from the keyboard, and while side 1 is positive, we're going to process this hypotenuse triangle by prompting the user to enter side 2's value. Side 2 is assigned a double from the keyboard. System.out print formatted, print your formatted string. We're going to print a floating value and a new line and a new line. We're going to call hypotenuse, which will return a double result. Hypotenuse is the name of the method. Notice there's hypotenuse, the name of the method, open paren, there's no space. That tells us that it's a method name. And we're going to send the current two double values, side 1 and side 2, to the method. Now, execution suspends and control is passed to the method. The method header is public static, so we can call this method within our static void main program. It's going to return a double type. The name of the method is hypotenuse. It expects two doubles with comma delimiters to be passed to it from the calling environment, and we did. We have side 1 assigned and side 2 assigned, both by the keyboard as type doubles. Within the hypotenuse method, we're declaring the hypotenuse squared variable to be of type double, and it's going to be assigned the result of math.power side 1, comma 2, which results in side 1 being squared. We get a double result. We're going to assign that double result to plus math.power side 2 raised to the second power. That will calculate a double result and add it. The final result will be the addition of the two double calculated results from math.power and assigned to hypotenuse squared. A reminder now is that we're not trying to determine hypotenuse squared length. We're trying to determine the hypotenuse length, which would be the square root of hypotenuse squared. So we're going to return as a double the result of math.square root of hypotenuse squared. That's the end of our method. A value is returned as a double, and execution is suspended, and we return to the calling environment where we called the method. The method call has been executed, and a double result is returned, fit into the floating point precision for our formatted output, and a new line and a new line. We then print a very nice reminder prompt to the user to enter side 1 or some negative value to quit. Side 1 is input via the keyboard as a reassignment to the variable condition of the while. At some point, the user will type in a negative value and will return to the while loop. The condition will test false, and we'll exit the while loop, and we'll exit main. This is our main method. We'll exit main and pass over the methods. They're only executed when called by name within the main program, and we'll end class triangle. So let's run the program. Enter side 1 a negative value to quit. Well, my test data on page 239, triangle 1 has side 3.0. Enter side 2 is 4.0, and it calculates the hypotenuse as 5. Now remember your formula, side 1 squared plus side 2 squared is equal to c squared. So 3 squared is 9, plus 4 squared is 16. 9 plus 16 is 25 for c squared, and we ask for the square root, which is the square root of 25. The square root of 25 is 5, so the length of the hypotenuse with side 1, 3, and side 4 is 5. Let's try another one. Our test data on page 239, triangle 2 is 5.0 for the side 1 and 12.0 for side 2. And again, side 1 squared is 25. I better get the calculator now. Side 1 squared is 25, and side 2 squared would be 144, and that totals 169, which is c squared. The square root of 169 is 13. So far we're testing pretty good. Our next sample data, side 1 is 8, side 2 is 15, and it calculates that the hypotenuse is 17. Well, 8 is 64. 8 squared is 64 for side 1 squared, plus side 2 squared. 15 is 255, I think. 15 squared, 225. 225 plus 64 is 289. So the hypotenuse squared is equal to 289, and the square root of 289 is 17. So the test data works. I'm going to type in a -1. Any negative value will exit the while loop, and we will exit the main method and exit the class. So we had a little bit of algebra, a little bit of geometry, and we're introducing our math classes within program assignment for chapter 6. So that is your syntax and logic reminders for Prog 6. I'd like to remind you to view all of your videos before watching my recorded lectures. And I'd just like to take a look at figure 6.6. So I'm going to file, close all projects, close my output window, file, open a new project, and I'm looking at figure 6.6. Figure 6.6, and open the project. And in my source packages, I have random integers.java, and this is figure 6.6 source code. And let's find that in our book here. Page 215. So random integers.java. Now, in the previous discussion, I'm overlaying what the author will talk to you about when he dissects the program in your video companion website. But some things I just want to highlight or emphasize. We're importing java.security.secure random. Notice that that's secure uppercase and random uppercase. And we're going to be using the class secure random. So we need to import that or fully path when we use a method from within that class. Now, secure random is a rather new class addition for security purposes to Java, and it does come with some overhead. Secure random does require some extra time and calibrations to process and guarantee secure random numbers. Unsecure random numbers in the past were generated by some type of generating startup, like maybe your clock, and could be regenerated or easily hacked. So it was an insecure piece of code that's been found to be intolerant for hackers, and thus secure random class has been fine-tuned and refined and upgraded, and now we are guaranteeing that we will be actually receiving random numbers when generated with secure random. There's more information about that. So we're going to loop 20 times. For int counter equals 1, while counter is less than or equal to 20, we're going to increment counter by 1. Our for loop body, pick a random number from 1 to 6. Now remember that when you are using randoms.nextInt, we have a value which is from 0 up to 6 that will be returned. 0, 1, 2, 3, 4, 5. 0 up to 6, 5, or up to 6. So not including 6. 0, 1, 2, 3, 4, 5. So random numbers.nextInt will return a number 0, 1, 2, 3, 4, or 5. And then if we add 1 to it, we're simulating results of 1, 2, 3, 4, 5, or 6, which actually are the face values on a dice. So we're kind of setting ourselves up for writing some code that might simulate dice games. So if you roll the dice, you want a value of 1, 2, 3, 4, 5, or 6 to show. Dice are not labeled 0, 1, 2, 3, 4, 5. So to accommodate, we're going to offset by 1. We get our results from random numbers.nextInt 6. That will return a value 0 or 1 or 2 or 3 or 4 or 5. If I add 1 to any one of those results, I'll be scaling from 1 through 6. And that simulates rolling a dice, if you will. We're going to output the face value. If counter is divisible by 5, start a new line of output. So we want to have 5 outputs on one line, one row. This is a way to control new line with multiple pieces of input on a line. So we're going to have 5 face values on each line. If counter is divisible by 5, start a new line of output. If counter mod 5, remember you have an integer mod 5. 5 goes into the integer value evenly. We're looking for a remainder of 0. So if counter is mod 5 with a remainder equal to 0, then that's our 5th iteration. We're going to start a new line. And I guess you can see the simulated output. We have random numbers simulating our dice face values of 1, 5, 3, 6, 2. We printed 5 outputs on one line. Our counter then is mod 5 with a remainder of 0. It is divisible by 5. So we trigger a new line is printed, and we get the next 5 face values, triggering a new line. So we're placing 5 output values on one line of text, and then we force a new line. We run the program again, and we get different random numbers. If you run the program again and again, you'll get a different set of random numbers. Well, then that leads up to figure 6.7, where we are actually rolling a dice. Figure 6.7. So I'd like you to spend some time in your study time looking at the logic of this program, and I believe it was assigned as a video companion author dissection that you should be watching as well. So certainly the feedback from the author is important. I'm just kind of pointing out some additional features of the program. So we're going to import java.security.secure random guaranteeing that our random numbers will be indeed secure and randomly generated. Public class roll die and our end class. Public static void main. We have random numbers object will produce a secure random number. So secure random is a class object. Our variable name is random numbers, and it's going to be a new secure random object. Integer frequency 1 is initialized to 0. Integer frequency 2 is initialized to 0. So our counters, counting the frequency, the number of times that a face value is rolled on our dice, are initialized to 0 and declared to be of type int. So we're going to keep a tally count for 6 million rolls of our dice. And we want to keep track of the number of times that the face value of 1 was rolled, face value number of that 2 was rolled. We're keeping a count of the number of face values rolled with that many rolls. So we're simulating 6 million rolls of our dice. We're tossing the dice 6 million times. For int roll equals 1, while roll is less than or equal to 6 million, we're going to increment by 1. Integer face value, we're offsetting from 0 to 5 by adding 1. We get the face values 1 through 6. So face will generate a random number and be assigned a value 1 through 6. Face will be assigned a random number, a random integer number from 0 to 5. That random number from 0 to 5 will be added to 1, which simulates the dice values of 1 to face value 6. So face will be assigned a integer from 1 to 6. Then we're going to use face variables current value to determine which counter to increment. So we're going to switch on face, and face can be a value from 1 to 6. So our switch lives within the control of the 4. Switch on face. Our first case is if the face value is assigned 1, we'll match on case 1, and we want to increment the frequency count for face value 1. And break. We go to the end switch and return. We go to the end switch and return to the 4. For int roll, this is the next roll of 6 million rolls. Face is assigned a new number from 1 to 6 randomly. We're going to switch on face's value. If it's 2, we'll increment frequency 2 and break out of the switch. If face matches 3, we'll increment frequency 3 and break out of the switch and return for the next face assignment until 6 million rolls have taken place, and we've been accumulating the frequency count for the number of face rolls on our dice of 1, 2, 3, 4, 5, or 6. We're done with the 4 statement. We're ready to print out our results. So print out a print line face. We're going to use the tab feature. That's a \T. \N, of course, is our new line. Here we're using a tab. We're going to print frequency. For a header, print formatted. We're going to format this frequency. They are integer values, so you see your %D. We're going to use our tab to print a nice, well formatted output report. We're closing main, and we're at the end of the class roll die. The sample output then, we're printing string face tabbing for string frequency, and then we're printing 1 as a constant. We tab for the frequency 1 current value, new line, print 2 for the face value count of 2 on our dice. It rolled a count of frequency 2. We're outputting frequency 3 count, frequency 4 count, frequency 5 count, frequency 6 count. If you run the program again, you'll see that the face values that were generated with a simulated roll of the dice are different. So let's look at code. Close all projects. File, open a project, and I want to open figure 6.7. Open project. And sure enough, there's my roll dice source code, and it has opened in the editor. Rolldice.java, public class roll dice. I'm importing java.security.secureRandom. We understand it will generate random numbers. We're guaranteed of that, but it does come with some overhead expense. It takes a little longer, and it costs your primary memory and time, so we have to make some of those decisions at times. For some of our little game features that we run, maybe just random generation is fine. Secure random does come with overhead costs. Public static void main is our program. Let's run it. And sure enough, it generated face value 1 and kept count in frequency 1 of the number of times that face value 1 was rolled on my simulated die. Face value 2, and kept track with frequency 2, the number of times that our face value 2 was generated. Face value 6, this is our frequency 6 counter, and face value 6 was generated that many times. So let's run again, see what happens. And you'll see that there's a new generation, and the numbers are different counts. So our dice are generating different counts each time we run the face values of tossing a dice. So I'd like you to, again, take a little time to study code figure 6.6 and 6.7, particularly for this chapter 6. All right, that finishes chapter 6. So soon I'll be putting together your lecture for chapter 7. And thank you very much.